Welcome friends. Today I am going to discuss the 14th class on GPS surveying. In today's class I like to take up further on GPS data processing, and under GPS data processing we will be talking on baseline processing. Now this class we will like to first discuss on the introduction, that means I will like to say about baseline, that is processing, and finally I will like to let you understand how the baseline processing is being carried out by taking a single code pseudo range GPS observable, from which we do end up with some parameters which is required to find out the baseline. Now in case of GPS surveying, baseline is the most fundamental unit or the primary unit that is considered in GPS surveying. So it is a very important thing to know and understand about its processing, how do we arrive at the baseline parameters. Now whenever we go for relative mode of GPS surveying, we do end up with some baseline. Now as you remember in my previous some other classes, I have told you that in case of relative positioning we take a location which is known as reference station. That means reference station means the location of this point is known. So at this reference station we set up an instrument, GPS instrument, and so it is called reference receiver. And corresponding another receiver we take, suppose this is the point whose position we want to find out. So this position is considered as rover station, and a receiver is placed on this rover station, and in this case we call this receiver as rover receiver, and this is a station whose position is unknown. So known, if we say XR, YR or REF reference and ZRF are the location of this station, that means these parameters are known. And if we say X rover, Y rover and Z rover are the coordinates of the point P, which is the rover station, these are not known. So we have to find out. Now in through baseline processing actually we do, so if we see this is in elevation, if we see it in a planimetric view, so corresponding to this point this is the station, and corresponding to this point this is the station. So this is the reference station, and this is the rover station, and the line joining these two stations this is called baseline. So we are to find out the parameter of this baseline. So if we say that the location is RF like this, R Y R E F, Z R E F, then X Y Z. So, we want to find out this. Now, if the difference is given by del x, del y, del z, then this x rover will be x reference plus del x, y rover equal to y reference plus del y, z rover equal to z reference plus del z. Now, you can see here that these parameters are known. We want to find out these x, y, z. Now, if we know what is the value of del x, del y, del z, then we will be able to get x, y, z. So, these del x, del y, del z are the parameters which define this baseline. So, it is called baseline processing. That means, by finding out the parameters of the baseline, we find out the location of the rover station. So, it is called baseline processing. So, in baseline, by baseline processing, in baseline processing actually we do find out del x, del y, del z. Now, after finding out this, we will be able to get the location of the rover stations. Now, what happens in relative positioning? The signals from numbers of satellites, like suppose these are the satellites, there may be n numbers of satellites, m numbers of satellites. So, and suppose all these satellites are visible from this reference as well as this rover station. That means, signals from all these satellites are arriving to both reference and rover stations. So, it will be coming like this. So, signals are coming. So, there may be m numbers of satellites. Similarly, signals are coming to this. From both m sets of satellite, from all of this m satellite satellites, signals are coming to both reference and rover receiver. Now, and as you know, in these signals we have 3 types of carrier phase observable and 5 types of pseudo range observables. Now, all these individual components may be made use to find out this baseline parameters. Either it can be used individually or it can be used in multiple way. That means, we may use a single code or we may use multiple code observables, or we may use a single code coupled with carrier phase observables, maybe one carrier phase observables or maybe more than one carrier phase observables. However, for all processing, as I told you in point positioning, it is that we go for code, single code CA observables processing as the most fundamental, and that is required. Anyway, so depending upon the components of the signals that we will consider, or depending upon the method of serving, like in this case suppose both are static conditions, so we call it static serving, it may be kinematic serving, it may be stop and go, as you have learned in earlier classes. So, whatever is the mode of surveying, ultimately fundamentally that we have two sets of observation. One set will come from the reference station and another set will be coming from rover station, and that set we will be considering only the CA code observables of the reference station signal and the CA code observables of the rover receiver signals, and that those observables will be used to find out the baseline parameters. Now, as you know that the pseudo range observable from satellite I, any satellite suppose I, to our reference receiver REF at any epoch t can be given by the geometric range of the satellite from the receiver reference receiver at the epoch t plus the receiver clock error. We have used the symbol del t reference, then the satellite clock error. So, error, then the ionospheric error from satellite to receiver, reference receiver, then tropospheric error, then receiver hardware error, then satellite hardware error, then multipath error, then random error. So, all these constitutes the, so this is how we do define the GPS observable. This is the parameter which we get in the GPS signal, but this signal GPS observable actually consists of all these constituents. Similarly, if we take the pseudo range of the rover receiver from the same satellite, but only to the rover receiver at the same epoch of time, we will get similar expression. So, ionospheric error, tropospheric error, rover receiver hardware error, satellite error, then multipath error. Now, this is also known, these two are known, these are known. Now, if we take the difference, so P, that is what is our relative positioning. So, which is known, because both are known, so it is known. So, will be equal to our difference in geometric range then your say into receiver and reference clock error, then these two will cancel out. So, and the ionospheric error difference then tropospheric error difference between reference and rover, then our difference of receiver and reference and rover receiver hardware. These two will cancel, which are the satellite hardware error. Then multipath error is also will be there, and of course that random error will be there. So, though these errors will be minimized, but we do not know about this anyway. So, this is the known part. So, this can be written as pseudo range reference comma rover from the same satellites I at an epoch t. So, this is known. Now, as you know that the reference station is known, means we know the value of XR, X reference, Y reference, Z reference. This is known, and since the satellite position of the XI, YY, ZI, this is also available from GPS signal. So, it is known. So, both of these are known, and as we know that the geometric range of the reference receiver from the satellite is nothing but square root of X reference minus Xi whole squared, Y reference minus Yi whole square. So, this is known. So, in this expression this part is known, this is also known. And this is the thing which really we want to find out. Also this part is not known, this is also to be determined. So, the expression may be now changed to PR reference rover I t minus reference I t. This part is known again, is equal to minus of rover t plus C into clock error reference rover, this is also known. So, and for others, for rest of this, let us consider it an error term E. So, whole of our GPS baseline observations can be reduced to this expression. This is the expression we get. Now, as we already told, the X rover is equal to X reference plus del X, Y rover is equal to Y reference plus del Y, Z rover is equal to Z reference plus del Z, where x, del x, del y, del z are the baseline parameters. So, this can be expressed as, this is known. So, this can be expressed as a function of rho bar with respect to del x, del y, del z, both of these together can be expressed like del dt suppose. So, our whole relation now is can be considered as some known parameter this and a function like this and an error term this. Now, if we remember in the last class, we have seen in a single code GPS processing, data processing, we also arrive at same expression pseudo range. This is known, and this is the expression, a function based on the receiver position and the clock error receiver and an error. Now, here is also, this is the relation, similar we can get it. Now, here we can, now this is the equivalent expression, but as it is non-linear, so also this is non-linear, because our this function is square root of this. So, now we have to convert this to a linear function, first we have to linearize it and we have to develop a linear model, then we will solve it by least square method. Now, if we want to solve this by least square analysis, this nonlinear model or this nonlinear equation first has to be linearized, then has to be develop a linear model, then we should go for least square analysis method as we did in single code positioning, and we can do in the same way, only in this case the parameters are del x, del y, del z, which is the error between the assumed value of the receiver and the correct value of the receiver, but in this case this is the baseline parameter. So, and in this case del x, del y, del z we had to made it to 0 through iterative process, but in this case we have to find out the value of del x, del y, del z as the unknown parameters. So, this is the fundamental difference, otherwise the mode of linearization and the development of the linear model is identical with that what we find in single code positioning. So, you can see here in the similar way we have to proceed in this case also. So, here also we will end up with ultimately an observable equation is equal to Ax plus E, where is the residual observation, design matrix, this is the unknown parameter matrix and this is the error matrix. Now, in this case the residual observation is this one, and your design parameters will be that unknown parameters will be our del x, del y, del z, del t, where this is the baseline parameter, these three are the baseline parameters, and it is the time parameter and this is the error. So, this is the thing what we did, we knew in the last class I have explained all this thing. So, now you can see here that this is the observable equation that we get, or the linear model we have developed out of the observation equation. So, here the observable equation for a single satellite, the signal coming from a single satellite is, this is the observable equation linear model, and for m satellites this is the relations we have derived in the last class. So, which can be converted to this is the in matrix notation, and this is the linear model, and this linear model has been used to find out the unknown parameter x, the position of the receiver, by using least square analysis, normal equation method, and we have end up with this. Similar to this, in case of baseline processing also we had end up with this relation. So, this is the nonlinear equation that is based on single code GPS observable for baseline processing. Now, since this is a nonlinear type, so using the identical way what we did in the single code point positioning, this nonlinear model first has to be linearized and then end up with a linear model like this. Only difference is that this x is the baseline parameters. Now, this observation metric that observable is that of the dimension m into 1, where m is the number of satellites from which observables are coming, and a is the m into p, suppose p is the number of unknown, so which is 4 in this case. So, I can write it equal to 4, and x is again 4 into 1, and the E matrix is having the m into 1, that means one error associated with each satellite observable. In case of baseline processing, another important difference from point positioning is that in case of baseline processing we go for weighted least square analysis. Instead of simple, we do give some weighted least square analysis. That means we do provide some weight to the observables coming from satellites. So, observables from each satellites are not having the same quality, they will be having the different amount of errors. So, their weights will be different, the satellites having less error, observable will be more weighted, and vice versa. So, by using the weighted least square analysis, we do get the unknown parameter matrix is equal to ATW A inverse ATW O. So, this is the final output that we will get in case of baseline processing. So, where W is the weight matrix, and it depends upon the quality of the observable that is being received from the GPS satellite. With this I want to conclude today's class, but before that I like to summarize today's class. Baseline is the most fundamental or most primary parameter in GPS processing. So, it needs to be taken into account with importance, with high importance. Now, whenever we go for relative positioning, we do end up with some baselines, and depending upon the purpose for which the relative positioning has been done, the quality of baseline has to be looked into. We do have baselines of different types depending upon the methods of surveying or depending upon the type of observables that we will take for processing the baseline. There are many methods which may be used to process the baseline, of which the least square analysis method is the most widely used. So, we had in this class we had discussed about how to process the GPS data to end up with the solution for baseline parameter using single code GPS observables, and at the end of this baseline processing we end up with a parameters which defines the different components of a baseline, which further may be added to the original reference coordinate to find out the location of the robot receiver. Thank you. Hopefully we will meet you next class again, and in the next class I am going to discuss on quality assessment. Thank you.